You'll start.
I'll start.
I will start.
So I just have to change the slides, right?
Yes.
Okay. So good morning, everyone. It's my pleasure to introduce Professor Arrvindh Shriraman, who's a faculty member at Fraser University in Canada. Arrvindh finished his PhD from Rochester in 2011, and before that he got his BE from SEC College from Chennai. And he had a successful startup in between. Today he's going to talk about hardware and compiler.
All right. So essentially, I start with this slide. So you get this left version of the talk. If my student gets it, probably give the right version. Hopefully, I'll successfully marry some portion of the left and the right. So essentially, I'm not a compiler person. First, I know there's some compiler folks sitting in the audience. I'm basically a hardware person. My Chisel compilers actually was just by chance. Like, even when I did my grad school career, I was all in parallel programming and stuff. Like, I was not a hardcore compiler person. Then there were some interesting problems that came about, like, my student wanted to work on, and then that's how I kind of got started with things like IIRs and stuff. Everything I speak about today is all open source, so we try to keep everything public in the public domain so people can access and try out. I actually forgot to change. I gave a talk at NUS before I came here, that's why I see it. I should actually say IISc, but it's the same talk. So if you saw, I don't think the NUS guys recorded it, so I don't think you could have seen this talk before I came here. It's all my list of students or PhDs that have graduated over time. The body of work that I'll speak about today, kind of started back in 2016, 17. So it's about 5-6 years worth of work that I'm trying to compress down to a short talk. And I'll kind of tell you how they're all related. Most of this work, so first just a little bit of a backstory. Just started with a lot of frustration back in 2016, 2017 on my side. Essentially, people are looking at domain-specific, it was not called domain-specific architectures back then. Back then it was called accelerators 6 years ago, people were looking at custom circuits and stuff. So most of the faculty are okay, I used to tell my students, let's build one. We didn't even know for what we were building these. We just knew we had to build some custom hardware. And then, they would spend 6 months, maybe a year analyzing the benchmarks. Each student had a different, interest in different application domains. They would spend another 6-7, year almost building a bunch of components, RTL, Verilog, that kind of stuff. Then another 6 months, you're putting things together, and then, finally performance tuning. And this is all very conservative, right? So the timelines I'm putting out here are very 6 months could easily end up being a year. And so basically this would be like one PhD student's pipeline, right? And then along the way they would publish, short papers every, step. And then a new student would come along and then rinse and repeat, right? And this was a very frustrating pipeline for me, where every time a new student came along, it almost seemed like all the learning that the previous student did, nothing carried over. They all seemed to have to repeat, this benchmark, this library, this whole pipeline. And so this is how this work kind of got started. I essentially did not want this pipeline. I'm very unhappy with it. Very serial. Didn't feel like learning transferred from one student to another. People were kind of repeating this. So our backstory is back in that 15, 16 time period, we started off by saying, let's accelerate something. So we started with that. And then, we started looking at, what should we accelerate? So we didn't know, back then, you would spend a year just looking at benchmarks, trying to manually, identify, regions. And then failing miserably because there would be branches. For example, our first work, we were looking at accelerating, spec workloads, right? And it was like a nightmare, just trying to do this. So then my student quickly started looking at front-end compiler work. So basically a lot of, hyper block formations, tracing, things like that, just to kind of identify where the regions were coming from. And so we did a lot of work there. Then we realized that memory ordering was a problem. So, we tried to solve that with alias analysis and those kind of techniques borrowing from compiler land. And then at some point we were trying to build the hardware and then realized that this was not a very profitable thing to do, because in this model, it kind of seemed like garbage in, garbage out, right? So most of the time we were failing, not because our techniques were bad, which they were very primitive, but we were failing because the workloads were written in really challenging ways, right? So if you give an arbitrary C, C++ workload and tell somebody go, build, accelerate this or speed this up, right? It's a very challenging task to do. And so we also saw like around then that there was mass movement, TensorFlow had come around, matured, and people were moving towards DSLs and it seemed like Allied had come along, like image processing libraries were coming along. And it seemed like they had matured to the point at which we wanted to kind of shift and start looking at more, those kind of applications. And so we did that. So we kind of, instead of going fully domain specifics, we went intermediate. So we started looking at Silk and dynamically parallel languages, not just going serial and start building like hardware from there, the parallel accelerators from those. And those look quite different than taking loops and then parallelizing them and mapping them down. So yeah.
Why was the choice?
Oh, why was the choice? So we needed a. Yeah, so it was basically a pragmatic choice. So we wanted so we at the LLVM-IR level, so we were starting to do a lot of this work within LLVM-IR. And so we wanted the parallel constructs to be in the IR, embedded in the IR, and not just as intrinsics. And Silk, so it was not purely Silk, so they had released this taper infrastructure, where they would add essentially fork and join IR instructions to the base LLVM-IR. And embedded in it. And so then it was very convenient for us to leverage a lot of the passes, extract, and do, keep our framework in place. That's the reason that we did that, as opposed to go the OpenCL route. The other reason was also OpenCL. Obviously, we wanted to look at places where custom silicon would help, right? And so our opinion was that OpenCL already had an awesome substrate in terms of GPUs. So the gains of trying to beat a GPU was not something that we wanted to take on, right? We thought that if we could enhance or build parallel machines for newer application domains, then that would potentially, be a better bet. And so in this case, Silk and other things were suffering from large overheads in their runtimes because they were being mapped to threads, and their Silk runtimes were quite expensive. So they're cactus stacks, and they had these, basically, they were finding it hard to run like large amount of tasks. Yeah.
I mean, Silk is uniquely it's mainly sort of dynamic recursive parallel. So what you can express with Silk is not natural with other things like OpenMP, OpenCL, and so on. So that's, and you do need dynamic scheduling and all that stuff.
And so we were targeting applications that we wanted to map those applications down to hardware. So like the ones which are dynamic, like you said. So that was also one of the reasons we did so. Right? So that was the unique proposition at that point. Right? I lost my train of thought.
You're talking about runtime overhead.
So our question was, so if you could make dynamic task overheads like 0, what does that mean? Right? If I could fork and create tasks at almost negligible cost, then what kind of programming models, what kind of applications could we potentially now enable, right? And so that was one of the things that we looked at over there. And it was kind of an interesting viewpoint. So in the sense that I think our conclusion was that dynamic task creation was not that expensive. Like you could throw the hardware at the problem. It was not the primary overhead. The data movement typically kills you, right? The fact that you can't statically analyze all the data movement and lay out the data the way you want to, like in languages like that, was the killer. For forking the task itself was not like primary overhead. And then we, back in 2019, MLIR was just starting off back then, so we didn't have that infrastructure, but we were dabbling with okay, how do you actually generate RTL from these languages? And then we realized, there's all these hand optimizations. So we would go from Silk to some base version of the RTL, and then hand optimize a whole bunch along the way, haphazardly until it kind of performed okay, right? And so then we started looking at, okay, can we make the optimizations themselves structured, right? And make it more like an IR, more like a compiler kind of thing, right? And so that's what we did back in 2019, after we built off the Silk work, right? Based on that work. That'll be kind of the core stuff that I'll talk about today, that you'll see. Then from there, we went to 2019, we started looking at, okay, so we were doing quite okay with dense stuff. So we started looking at sparse stuff. sparse data, and then we started looking at sparse generators, right? For instance, like as a specialized thing. So we're building like IRs and generators just for sparse matrix multiplication, for instance. And then now we look at like, we forked off of that, like to now look at like, generating caches, for instance, not just generating like, compute side of things. And then now our latest work also looks at things like dynamic instrumentation, where we kind of take the circuit that we produce and then we add in like probes and things into the circuit based on what needs to be done and what the user wants to do. And then we'll take that whole thing and then map it down to like an FPGA, right? With the probes plus like some checkers plus your original design onto the FPGA. And then so you can dynamically check things and monitor things as to what's happening on the circuit. And so we were using this to kind of iteratively debug, right? So kind of like Valorant, but for hardware, right? And so that's kind of our latest work. So I can talk about any of these things, but today I'll kind of talk about our experience basically with this IR business, some opinions based on what we've learned, right? And then also some of the debugging work. We'll see how far we get through, but usually I don't try to complete the slides. I go slow, and if you have questions, just stop, ask me, and a lot of this is based on our experience. It's different people have different experiences with this thing, and so I'm curious to see what other people's opinions are on these things and so on. So stop me whenever you feel like. Right? This is just so this in order to show you kind of what our design kind of looks like. So this is just our a high level overview, a couple of slides on like where we think things stand and why we don't do it one way or the other. So back in like 2011 or whatever, when I had first graduated, they had this NSF workshop panel that they had organized, and people had spoken about punching through like layers between the software and the hardware, and how do you do co-design and that kind of thing. At the initial wave, most people actually eliminated the layers entirely, right? So if you looked at the initial wave of like accelerators, people just went directly from algorithm to like architecture down to the, and maybe they went to the RTO, maybe they didn't, but they definitely eliminated a lot of the layers in between, right? This is actually, retrospect was a bad thing. Obviously back then, I think they understood what the cost was, but they couldn't quantify it. But I think that subsequently, a lot of people have gone through this quantification. We basically dub it like premature acceleration is the root of all evil, meaning that you really should try to not think about whether you need to accelerate or not in the first place, right? Because there's a lot of costs associated with the software bring up. In fields like ML, it's already pretty hard. If you step outside one of these hot domains, it gets really hard to bring up all this software infrastructure. And so that is a problem. And you kind of need the whole application to work, not just one single IP or like one single execution unit to work. So you kind of have to integrate the whole piece, and that becomes an expensive part of the component. Hardware design is hard. So this is not just about like RTL being hard, meaning like at the gate level. It's just that as things get lower and get more funky, and you got to change the microarchitecture in response to that. So it's not like we put out the architecture and then go do all the gate level optimizations, and then you get the hardware, right? Your lower level technology is going to start feeding back all kinds of things that they can or cannot do. They could, for example, inform that wire density is too high, right? And instead of them going and fixing this, you may need to make fundamental changes in your architecture. Like maybe you have for one example, one concrete example of this is in some places we had done a lot of, initially when we did the optimizations in hardware, we had put out a lot of static networks, meaning that there was a lot of, it was very wire dominated and wire heavy, right? And we did this because it was just easy to manage. We didn't have, when we were generating things like NOCs and networks, like in your circuit, like it's a lot easier to just stamp out a bunch of static circuits for each one of the traffic patterns that you really care about. It's much harder to do VCs, get them to share the physical link. So we just stamped out a bunch of like independent physical networks. And then we later realized that as we were doing the synthesis and backend synthesis, that this was a terrible idea, like for some of these newer technologies, and we were basically not meeting timing. And so then we had to go back and basically convert a lot of the static networks to dynamic networks, meaning buffers sharing like common links, like wires, so that you can channel the traffic, multiple traffics through like common links, right? And this a whole new beast of like problems for us, right? Yeah.
Some of these problems come because you try to do certain optimizations at a level,
yeah, so we typically
programming it at a higher level.
No. So in this case, the higher level, we already know what the patterns are. So for example, each tensor, we said, okay, these are getting fed in this way. So they just dump out one static network. You don't need routing. It's just a bunch of muxes. Really dirt cheap, right? Or at the architecture level, you think it's cheap. But then once we use so there are newer tools now like OpenRoad and bunch of open source like timing tools and synthesis tools where you can take the RTL you produce and quickly within a day get reasonable floor plans, reasonable timing. You don't need, right? And you get feedback saying, oh, I could only meet timing at 300 megahertz or something, right? So I couldn't push the clock higher. So you get that feedback and then you look at where the density is and you see, okay, all the wires are kind of dominating. And so you take that feedback and then go try changing, tweaking the architecture, right? So it's the lower level feeding back what's feasible and what's not feasible at a certain technology, right? So typically we'll do synthesis at 45, 7, which is all the predictive open source technologies, right? That they have libraries for. And then we'll see whether what's dominating or not, and then feed that back to the architecture. Once you feed it back to the architecture, from there onwards, it's coaxing, cajoling, human ingenuity, however you want to call it. It's not or do these optimizations and then suddenly you're going to meet timing. It's we can make it easier for them to do the optimizations, but it's still kind of it's art more than science, I would say, right, at this point. Okay, any other questions? Yeah, so this is one. And then also the gains you see due to the architecture are very, the curves are not linear or even predictable, right? So most often you get these initial bumps and then you kind of what gains you see will vary entirely on your application, what architectures you brought for it, and so on and so forth. So this was a paper from a few years back. We didn't write this paper. We wish we wrote this paper, but there's a colleague of ours that wrote this paper. And then they basically call it chip specialization return, which is, okay, how much gains are you seeing really due to the architecture and how much are you seeing due to the technology? And the main thing to take from this is the left is the CPU curves, the right is the accelerator or specialization curves. And the main thing to observe is that the specialization curves are just curvy. They're not like regular curves. And so our main goal is to navigate this, right? So be able to understand and navigate through this and not be a surprise, right? So even if you get only a 20% after the first 10x, we want it to be predictable, meaning we want to be able to understand that we're only going to get a 20%, right? So navigating these curves is one of our goals as part of this IR thing. So in terms of goals out of this is, one is you always keep the software to hardware flow because, and this is shared with things like ÄµIR or circuit at this point. We want to lower the barrier to specialization. So we want to enable CS folks, computer science folks, to be able to build this kind of circuit. Iterative hardware exploration. So this is one where we want feedback and then be able to change. And normally this is not as simple as just saying, change the path or change the optimization you're doing. Sometimes we want to add things to the IR itself. Right? We want the IR itself to be mutable. We don't. When you're doing the research, typically the first time you design the IR, it ends up being not as great as you want it to be, and you start incrementally changing things in it. And we want to be able to do that. And interestingly, the hardest part we found as part of this iterative process is the lowering process. Every time you change something, you have to write some kind of converter that takes that intermediate representation and then dumps out RTL from it. That's hard. You want that thing to kind of be streamlined because they are students, right? So they are, different students come with different levels of expertise. And then you want full application, meaning you want all of this to be integrated together, right? You're not just putting on one IP, right? So one thing that people do is basically they start with IISs or instruction level, 3-op views of these things, and then try to do this. So CGRAs are an example of this, right? And essentially, that's kind of every time the ISA changes, you got to redo this again. Is an instruction set the same as an intermediate representation, or intermediate representations are just instruction sets? There's a lot of different views on this. The compiler folks will probably have a better opinion of distinction between instruction sets and intermediate representation, right? But for us, it's just the fact that instruction sets were not extensible, so there were a few limitations. So for example, it only defines the what, doesn't kind of have operational semantics. You kind of have to actually generate hardware. It's not precise enough, and typically trying to capture hints at the ISA level kind of is hard. this is why, this kind of stuff is shared with MLIR, like kind of the goal. Like I said, some of this predated MLIR, like, before the MLIR became like circuit. For us, basically, we think of ourselves as a hardware microbrewery, kind of, so we mix different things together, and we want it to be extensible, tunable, the framework itself to be that, right? So this is what we call as this micro-IR flow. And I'll give you an example of this, and I'll also distinguish it with respect to MLIR and like, the more recent, works in that space, right? So essentially, this is what it looks like. So first of all, it is hierarchical, similar to MLIR. So in that sense, it's similar. There are a few important differences. The important differences are that for us, it is a dynamic graph, meaning it's not static. So when there's an edge between two things, it doesn't mean necessarily that that edge is going to be triggered at runtime. It based on the program logic, based on the conditions, the edge could either be spawned or not. Right? So essentially, the tokens, there are tokens that will travel along these edges, and the tokens are dynamic. And there are two kinds of tokens. There's a spawn and the sync, which is the same as your traditional dynamic parallel languages, right? So spawns, in this case, for example, I have purposefully used an example that truly does not showcase all the power of this language, but is more similar to traditional static languages, so that you can see clearly what the differences are. So here I have two nested loop. It's basically a simple, it's adding two tensors, like element by element. I don't actually know the size of the tensors in this case, so it's just an n. N could be anything, right? And we're trying to generate a circuit for this. So the way we would do this is first, we would generate like top level task blocks for each one of these loops. Each body of the loop is a separate task block. So in this case, for example, for the for I block, essentially this portion of it would be the task block. So basically the J and the body together would be like a task block. And this portion of it essentially is just controlling whether these things lower down get triggered or not. We will then add edges, and each of these edges you have tokens flowing. And the tokens are dynamic in the sense that during runtime, the token will be sent. So either it could get triggered or it could not get triggered based on what n is. So for instance, if n here is 0, then no tokens get sent, nothing gets triggered. If n is 10, then you're going to send 10 tokens down and dynamically trigger this. Once you do this, then there's a bunch of different things you can see. So the syncs are essentially travel in the opposite direction. So once these tasks finish, they coordinate back with their parent. And so now, essentially what this is, this hardware is showing you is a hierarchical, task graph, basically, right? And we've taken the task graph and then mapped it down to the hardware. We have not yet expanded what's inside each one of these blocks. We have only expanded what the tasks themselves are. So that's the first distinction compared to static approach, where, for example, in the static approach, you might unroll this loop some k times and then stamp out k copies of the thing, right? In our case, we won't stamp out k copies of tasks. We'll only stamp out one copy of the task. We will then subsequently, as we expand the hardware down and try to optimize it, each one of these tasks internally can choose how many executors they want, right? And they would stamp out that many executors. So that's the equivalent of your unrolling in software. So we're not unrolling the software and then stamping out the hardware. We're stamping out the hardware and then parameterizing the tasks. Yeah. So then in this case, this is actual hardware. So we're dumping out RTL. And so the IR compiler that we have, which translates this, would stamp out these.
Does it know the value of n?
No, it will expand it subsequently. It doesn't actually, it's because it's a dynamic graph, it doesn't actually need to know what the value of n. There has to be one executor in there, but that's sufficient, right? But then if you only have one executor in there, that's basically a serial execution. You're only running one body at a time. So what we would typically do is we would stamp this out and then lower down based on how much hardware resources you have. For example, we would mapping this to an FPGA. So we would decide at that point, once we have the caches and all kinds of things put in, okay, how much do you want to stamp out? You want to stamp out 5 units? You want to stamp out 10? Basically, it's a hardware configuration problem. It is not a HLS synthesis problem, right? So if you treat this as a static graph, then it becomes a synthesis problem. I first have to unroll it and do all that. But instead, what we do is we stamp this out and convert the synthesis problem into a configuration problem. Yeah.
So for every run of application, the configuration has to come.
Not every run. So this gets stamped. So when I say configuration, basically I mean how many executors are you going to stamp out here? Is this going to be connected to a scratch pad or not? Like there's a lot of optimization decisions that need to be made. So those get made by the compiler. You're spitting out Verilog or RTL, and then you're burning it into circuit. So it's not that you're configuring it. When I say configuration, it's the compiler configuring it before the hardware is built. But once the hardware is built, it's fixed. You're not changing it. Yeah.
In other words, you come up with a design with parameter.
Yeah, exactly.
Right.
Yes. Yeah.
When is the sequence? Is it that the spawn it starts one for loop, and when the full for loop is complete, then the sync is sent?
Yeah. So for instance, here, let's say that I=0 starts. So you send one spawn down, and then this would start n instances of the J loop, and these n instances of J loop will spawn n bodies down here. When these n bodies finish, they'll send one seed back, and then once the one seed comes back, this will send one seed back.
Okay, so every loop, how many instances it is allowed to start for the things below?
At runtime, it knows, right? At runtime, for example, you have a function foo, maybe that's on top of this, and foo is passed a parameter n, right? So at runtime, the n gets bound. So of course you know that.
So another question is, what is the advantage of doing it as a decouple? First unloading and then.
In a lot of the applications, like there's a lot of the applications you may not know it. Like I can show you, like in this example you do, it's conceivable you might know this, but in like many applications like compression, there's a whole host of these like deduplication. Like you don't actually know what the n is. And also in this case, you're only looking at this as a parallel for, but you could have applications that do a fork and then some work and then do another fork. Like imagine like you're doing like traveling salesman, or there are a lot of applications that are naturally easier to express using that kind of a framework.
Before the runtime, you have to figure out how many copies you want of the body on a certain number of threads in that.
So in this case, this is fully buffered. So let's say that I parameterize this to 8, and I sample 8 bodies of the executor. And this one wants to, so n is really 16, right? And so you really want to run 16 things. What will happen is the other 8 will just buffer, right? So we'll build all, this is like full generalized task model. So these queues here will buffer the tasks, and it'll all run correctly. It's just not going to run as efficiently as you want it, right? But then getting a more efficient design is pretty simple. If that's what you want to parameterize for, then go back and change one parameter, one word in one file, and then suddenly now you get an entirely different circuit, right? So that's kind of the thing here. Okay, but there's still more challenges. I've just shown you the simplest version, right? You see, like stamping of these actually is the easy part. Supporting these more the application is the easy part. The harder part is optimizing those tensor movements, right? So in this case, these look like loads. They don't actually look like DMAs or anything. So how do you combine the task execution with the streams or DMAs, and all of that is kind of the most challenging part of this. Which in a static system, you could have written this as, oh, I want to add tensor A and B and store it in C. In which case, you probably are going to get more efficient hardware if you could say that. Right? Yeah.
I actually do not understand the core idea. Is the number of executors decided at compile time?
Yes.
Or at runtime?
It's at compile time.
Okay, so then what is dynamic about compared to other?
Whether you choose to use the execution unit or not is the dynamic. So typically when you're doing it statically, you would bind when that task would run. So for example, like in typical static graphs, like let's say that you have those A's and B's, and they're not available in your local memory and fetching it from DRAM, and you end up stalling the load. They won't be able to handle that. For example, they not only bind the fact that it's 5 execute units, they also bind the fact that, oh, this the J = 0 loop is going to run on execution unit number 0, the J = 2 is going to run on execution unit 3, so they would bind the resources as well. We won't be binding the resources. The resource binding will all happen at runtime based on which is available, right? So in this case, for example, let's say that A=0 and B=00 are all in your cache, right? So then that execution unit is going to finish in a cycle or so. But let's say they were not in your cache. They may take 10s or 20s of cycles. So the executor unit that's running maybe A of 1, B of 1 takes a lot of time, right? So that unit is going to be busy. So all of those would be runtime.
Another round of recombination or something at runtime to decide which one you're doing.
Yeah, so you have a full dynamic issue. You're dynamically figuring out which execution units are free and you're issuing it to them, just like a processor would do, except instead of doing it at the instruction granularity, you're doing it at the task granularity.
There'll be an operating system that does.
There's not operating system. So in this case, circuit plus like a runtime. But it's not, runtime doesn't really do it. It's all in hardware.
I'm a bit confused with the terminology that combines static runtime and then the parametric and then gets instantiated.
Okay.
Perhaps it's terminology. I mean, the mapping can be. So there are various things going on, right? There's something that are known early, then there's something that are known late.
And something that you do early and some things you do late.
Right, but that's correct, right? During the compilation.
Yeah.
Mapping can be, I mean, you can have parametric mappings. But the thing that's not still clear to me is that N is, it's not, okay, so what is compile time and what is runtime? That's, N is still known, right? For you, when you're actually generating hardware.
I don't know N. N could be anything.
N. So it's a parametric design, and if you have some number of process, and it is sort of tied to execute that.
Yeah. It is not tied. I think that's where the difference. So we're not saying that the first 3 iterations of the loop will run on executor 0, 3 to 6 will run on executor 1. We're not saying that. At runtime, in the hardware, you're dynamically figuring out which executor is free and then issuing that iteration.
Extra hardware compared to other approaches.
Yes, there is extra hardware. Yes. So did you get that? So the mapping is dynamically issuing it. In a traditional sense, you would statically issue it, right? You statically say this has to happen at this time.
Right. So there's no closed form expression that says I goes here, but then dynamically.
Yes. Yeah.
Okay.
So you have bitmaps that kind of figure out which unit is free and then sends it there.
Sometimes the task scheduling on this hardware is dynamic, and that happens using the underlying hardware.
Exactly.
Yeah, that is definitely suitable to Silk and those kind of things.
Yeah.
You cannot do but then there are also lots of programs that statically.
You can. I'm not decrying that also. That's why I said for this example, most probably the static is going to be the best. Right? I just showed it so that people can understand the differences in the model as well. Right. Yeah.
Just to add to that one. So basically, since you are at runtime figuring out the slot in which specific iteration goes, you can just take the example of body. Each iteration of the body might have some local variables or even local variables in it. So since you're dynamically choosing this slot, that means you have to correspondingly dynamically choose the
Dynamically allocate things. Yeah. Yeah.
So I think that would also require like multiplexers, additional
Yeah.
multiplexers.
So what we would do is typically once we have this, it goes on to the IR. That's why tape is really important. We want this at the IR level. We create a closure. Basically, we would enumerate all the parameters that go in, how much is the local, what's coming in, and we would take the task and then create a closure from it. And then then map it down to basically what's like a coroutine. And so when let's say this task is locally, in this case there's no temps, but let's say hypothetically there were temps that were declared and you would have to allocate. Then when the task starts, we would allocate that. We will have like RAMs into which we would allocate space, and then you would use that. The general idea is that essentially everything that's required by a task, right? So local variables are allocated, globals that need to be passed in, all of that would be enumerated and kind of created along with the task. And so, for example, here, for instance, the variables I and j have to be passed in, the induction variables have to be passed in, so that you know which IA of ij are you processing really. So those we would cut and we would kind of feed it into the task. So for every task, we would generate like a task block, which is basically an enumeration of all the things required by the task, and then also all the resources. When the task first starts, we would allocate that and then pass those in, and then the task kickstarts. Once the task kickstarts, all the resources are there. The only thing it can stall for is non-uniform memory latencies. For example, this A stalled. It's not in memory. It's not in your cache, so I don't know how long it's going to take.
one iteration call that does not stop subsequent iterations.
No,
The other slot.
it'll use other slot, but that slot is gone. That slot is stalled for this thing. We do have another level of pipelining that happens. You'll see the next level when I expand one of these statements and what happens. Okay. Any other questions?
So just at a high level, like a hybrid between general purpose CPU and fully instantiated at compile time. Is it somewhere in between?
If it makes it easier for you to understand, you can think of it that way. Essentially, we are strategically saying we're going to spend extra hardware for dynamic issue because we think it's important and that we can support certain languages that previously could not be potentially supported. That's a better way to think about this, right? So most people will not. Sorry, I shouldn't say most people. In ML and other workloads, like static issues, like people can sign off on that because most bounds are known, all the matrix sizes are known, like you can schedule the whole thing. We are looking at alternative applications, not in the ML domain where you don't. Right? That's a better way to think about this. So when the body comes, we will then expand it, each of those ops, and we'll do pure data flow, pipeline data flow. So essentially data like I's and J's goes from the top, gaps are like pointers and basically data flow ordering. So this is where you can see that each one of these could potentially stop. Like this load doesn't know where the data is coming from, or at least we don't bind it at this point, right? Potentially, further down when we do the optimization, we would add a sketchpad and the load would fetch it from a sketchpad, in which case it's always going to be one cycle, right? But when the task and the flows are expanded, we purposefully prevent this load from knowing how long it might take, right? And so basically supporting more generalized patterns in terms of the memory accesses, but also precluding optimizations, right? So essentially, people who do TensorFlow or this thing quickly observe that this is a stupid idea to do this because if you are doing this, then you can't schedule the DMAs and the tiling and all of the other things you can do if you view this as a pure tensor, right? But then you'll see we generalize this. So by saying that this load could actually be support like tensor loads and other things in the IR, and so potentially you could then attach in those things like DMAs and tiling and all of the other aspects, right? But essentially, we don't do static issue. I guess that's the key. We don't ever line up like, okay, this has to happen at this cycle, right? And if you look at traditional FPGA flows, they would do that. There would be like a centralized FSM, and then like there'll be these ops, and then these FSM will essentially say, okay, you happen first, and then 2-3 cycles later, you happen next because I know that you only took 2 cycles and all of this stuff. We don't do any of that. Right? It's entirely dynamic issue, dynamic data flow. Okay.
How do you define a scheduling unit here, like the issue unit? What's the granularity? How close?
So there's two. So at the level of the ops, there is no scheduling. Basically, it's just latency sensitive ready value signals going on either side. So it's just the parent triggered, data flows through, and then the data essentially triggers. So you don't actually need any fancy scheduling there, right? We're spending overhead on the latency sensitive signals basically.
I see. And so each of those is like an LLVM instruction.
You could think of it as that granularity. But essentially we generalize this. So potentially we add other things to this. Like for instance, this load could be like a tensor. This plus could actually be a tensor unit. So in which case we could generate like systolic arrays. So there's some type-based like expansion of the hardware. But the first version we built, you're absolutely right. It's just an LLVM instruction. We were just synthesizing like simple programs, so we didn't need anything more complex. And then at this level, you have the buffers, the tracking of whether the slots are free or not, mapping all of that. So this is a higher level of scheduling. So there's 2 levels of scheduling happening here. One is at the task level, and the other one is at the op level. Right. And actually, there's more levels based on what each of those ops end up being. Right. So if you have like systolic array or something that is creating, if each one of those are tensors, then there's another further cycle level scheduling that's happening. Right. So there's multiple levels of scheduling. But scheduling is, we don't really do it in software anyway, right? So it's just whether we're choosing to have this as a task and whether we're dynamically issuing or whether we're doing data for issue or something like that. It's just what granularity you're choosing it to be. That's all. Right. So this is what our overall flow kind of looks like. So we right now at this point we go from paper or TF Lite, for instance, intrinsic. So we go through this this accelerated graph written here is the one I just showed you, and then we have a further low-level block graph, which I'll kind of explain in a second. And then each one of these will kind of be expanded using Chisel to kind of get the very log, right? So in terms of what our goals are, essentially, when our first version of the hardware may, this is what this code kind of looks like on the top, and this is kind of the hardware we want, but we want to get to it iteratively, and that's kind of the idea, right? So we want to not just, get this and then dump this out, but have like passes, just like a compiler would, to kind of incrementally kind of get there. So another way to view this work that we're doing is to kind of distinguish it from traditional work that has happened in the space, right? And latest work like circuit. So I'll say a couple of words about this to kind of say where in this space we are, basically. So the traditional, most, I wouldn't say necessarily even popular, but just one that the FPGA guys have kind of adopted for decades now is the C to RTL flows, right? So basically have some C code loops predominantly, add the pragmas, and then get the pragmas to control like the unrolling, pipelining, all of that, and then spit out the hardware, right? And this I would say is, mostly tuned towards software integration, meaning being that you can go from the C program to like the hardware maybe reasonably quickly. How good that hardware is, the jury's up for that. But essentially, they primarily focus on this software integration part. The other extreme is like these languages like Chisel and Spatial and all these like hardware, what I call is hardware construction languages, where they basically are like embedded DSLs hoisted on top of general purpose programming languages. And the goal there is they want to spit out some hardware, but when they construct the hardware, they want it to look nice, kind of have a software-ish feel to it. And these guys are going after, like, I would say, the performance tunability aspect. It's WYSIWYG. What you see is what you'll ultimately get in the hardware. It's very easy to tune. There's a lot of reusability, right? Because you can build in vast hardware libraries that you can leverage to quickly put things together. And the main disadvantage is the software integration part. They don't actually integrate the software, so you still have to build a compiler that kind of maps to the hardware once this whole thing is done. And then now, like subsequent, now you have works like circuit, which is like the latest and greatest in this flow, where basically it's if you add one sentence to describe it, it's basically adopting the MLIR methodology for hardware design, right? So where I would say that you get software integration and reusability, but tunability is where it kind of falls down. And I'll tell you where we think we fall in this spectrum. So this is like a graph of showing all the different IRs that they support right now. And the main thing is, first of all, you notice that it's kind of hierarchical. So you got the software-ish IRs that sit at the top, and then you got the hardware-ish IRs that sit at the bottom, and then from there you get to Verilog and circuits and so on and so forth. So one of the key challenges that we have encountered as we've done this work is that essentially you need converters that kind of need to convert from the software IRs to the hardware IRs eventually, right? Writing these converters is not an easy task. Right? Writing the converter itself, once it's written, it's awesome, right? Once your IR is fixed, once you write the converter, it's there. But how easy is it to write converters from the software-ish IRs to the hardware-ish IRs is where they kind of start to get flaky. Right? Particularly because you got to do this with grad students, you see, right? And they come with different levels of experience and they enter, and the hardware folks don't necessarily have all the the compiler view of things, and it gets quite challenging. The second part is how do you write optimal converters? Right, so these IRs that are the hardware IRs at the bottom are not necessarily optimal; they're really low level. For example, you want a systolic array. There's no way for you to say, "I want to take this tensor array and make it systolic." I don't want a data flow model because I think the data flow is too inefficient. So there's these two key challenges that arise, or at least we encountered when we went and started taking a look at circuit. Our opinion is that essentially this is all great, but this is mostly like an EDA tool. What you really want is to start from the input languages at the top. So these hardware construction languages are really awesome. They really help you write converters really fast. For example, if somebody gave you a adder and said, I want this to be a tensor add, build me a 4x4 adder or like a 4x4 multiplier. It's a lot easier writing it in Chisel
than writing it as a converter within circuit, right? And so that's where we plug in. So essentially, our opinion is that you want to keep the hardware construction languages in as part of the flow. So essentially, we basically feed into them, right? So our IR is hoisted on top of the Chisel, right? So instead, and then from there on, the flow is fine. From Chisel, you can go to Î³, and then you can use circuit. You can use these EDA tools. But essentially, if as a computer architect, if I wanted to easily, and if I want students to experiment with the IR and like be able to write these converters, then experimenting with the IR or introducing new IR constructs, MLIR makes it really easy. However, the hard part is writing the converters, particularly because all the conversions are written in like C++, right? Whereas if you use Chisel or language, more natural to kind of like these transformations or conversions, right? Notice that I'm not talking about the optimizations. I'm purely talking about I have this node in my hardware graph, and I have a lot of options when I expand it down to the RTL or the Verilog. Writing that transformation or conversion is a lot easier if you use languages like that. So unfortunately, Chisel doesn't have an IR. It's kind of like by definition, it's kind of like a domain-specific language. It's too imprecise to be an IR, right? It doesn't give you a lot of the concept, and so that's where that's kind of our position on this chart. All right, questions or thoughts?
I mean, ultimately, I have these front-end languages, and some languages are more suitable after they're more expressive for hardware design. So you just need the right level of abstractions to go from the yellow box to the ones below. And how you design those abstractions when you go through some of the other dialects that you showed versus design your own thing. I think that is what makes a conversion simple or complex and more effective or less effective.
If we had like an easy way, so right now from the conversion to go to the Chisel and then come down, then life would be awesome. Unfortunately, most of the converters, go down, they quickly go down the data flow or whatever, suboptimal, and then map it to the fertile. Right? They are trying to be alternatives to languages like Chisel. What we really want is to feed into the hardware construction, right? Because there's all these. It also gives you a very WYSIWYG way to do this. So essentially, when you have languages like Chisel, when you write the converter, you can see what's happening a lot more, visibly than if you wrote it as part of the MLIR like flow, right? Because you don't get to see what the intermediate until you get to the end potentially. Yeah.
Yeah, I guess you already answered this. I was going to ask why are you not going from IIR directly? Is that
so the main reason is that µIR alone is not sufficient. So the individual nodes, they come with a lot of constructs. For example, when we just showed you a load node, it's not just a load, right? So for example, we'll do alias analysis and figure out if it has to be attached to something else at the beginning, something else later. And then there'll be a lot of parameters. For example, like load width, there's a whole host of things that need to happen when you're trying to connect it to other places. Now, generating fertile for all of that is a lot easier when you use Chisel instead of writing a converter to go from µIR to fertile within MLIR itself. Right?
I used to think that fertile and Chisel we have similar level of abstraction.
No, not at all. That's almost completely incorrect. Right? So if you think of it that way, that's absolutely the wrong thing to do. Because Chisel is it's a Scala front end, because it's embedded in Scala, it adds so much more that, it's very different than, for example, let's say I want to dump out 5 executors. Like at the Scala level, that's just a range loop. I'm just going to put a loop and say, okay, I want 5 of these, right? The construction is so much more powerful using the Chisel. For example, at the fertile level, all the bit widths have to be expanded. For example, let's say I have 2 packets that I'm connecting with each other, and then one of them, this variable is data ends up not being used. Fertile, just at the Chisel level, you could introduce it, and then when you go from Chisel to fertile, the Chisel compiler will take care of on itself to eliminate all the dead wires. Whereas if you go to fertile directly, it's your responsibility to eliminate all the dead wires. Right? So there's a lot of things that happen when you go from Chisel to fertile that you just lose completely if you're trying to go to the fertile directly. In fact, you end up trying to replicate all the stuff that Chisel already does as a hardware constructor language, right? And so that's where that's where our opinion, the Chisel part is really powerful, right? The fact that you have a hardware language that at a higher level is very powerful, right? Okay, other questions? All right, so this is where we sit, and then the rest of it is pretty straightforward. So we have a whole bunch of optimization passes. So these ones are all pre-Chisel, right? So basically we do all these optimizations, and then we have a layer where all the Chisel libraries will plug in, and then we'll expand on all the environment. So, at this point we have like basic set of optimization. So for example, like doing hierarchical buffers, for instance. If you want to do like parallelism or replicate circuits, and then spread out the loops or even tasks. If you want a pipeline, for instance, so if you want to, each of those data flows you can treat as, okay, inside, and then I'm going to wait for the whole thing to come back, or you could pipeline, in which case, as the top level nodes become free, then you can start pushing more things. And then finally, we have these domain-specific ones where, again, this is where Chisel becomes even more important because it has things like type classes and things, a whole host of Scala constructs that you can essentially, for example, write one version of the systolic and then stamp on like FP8 bits or FP16 bits, or like you could expand the types. You could, for example, introduce new wiring in those systolics if you want extra ones based on to try for sparse matrices, or like there's a whole host of optimizations you can do at the Chisel level, right? And so that's where that kind of country shines, and that's why we think the Chisel is like quite important. Yeah. No, so in this case, this is just data flow pipelining. So in this case, you're starting multiple iterations, not iterations necessarily. You're just so remember you don't necessarily. So these are task blocks. Okay, so whether you have an iteration or not, you're just forking these tasks. And all we want to do is if something is stalled down here, we don't want it to block the whole thing. We want to keep pushing it. So it is similar to loop pipeline in some sense, but in this case, both is more similar to hardware pipelining, basically.
And what if you have like data dependence?
So we would handle that. So we would essentially, what happens with loops, we can go through, we would introduce like a loop header block, and then all the data dependencies will have fees, obviously at the beginning. So the loop header block will have a bunch of fees, and then the values here will go back and sit in those fees until the next iteration kind of starts.
And your dependencies via the SSA values. Let's say your dependencies via some alias.
So for those, that's what. So in 2018, we did this work where we said we would do alias analysis, and where it's possible to eliminate, we would eliminate. And where it's not possible to eliminate, we would have two options. Either we would introduce a wire and then basically slow or you basically take the penalty, or we would have this kind of speculative thing where as soon as you know the address, you would send out the address into the unit. And then that would do a comparison. And if the address mismatches, you would issue the access, right? Or you would issue the access, value will come back and it'll stay there until like this one verifies that it's okay. In the meanwhile, you're propagating values down to the lower levels until you hit a store point. Right, and at the store, we would basically stop it. And if the value mismatches, we just squash the whole thing. Right, so so we have optimizations like that basically stuck in. Yeah.
Do you do any kind of design space exploration here as well?
We do, but very primitive, right? So nowhere close to because the dynamic defining the space has been quite hard for us. Like. That's the penalty of the dynamic, right? It makes it really hard you push so many decisions to runtime that it makes it extremely hard to do design explorations, essentially, right, at compile time. Where exactly it kind of falls, ask me in 2 years' time, we'll kind of hopefully figure it out.
Because I was thinking that doing it design space exploration at a higher level is also equally important if you can do it, right, in terms of performance.
The memory really plays havoc with you. Right, so essentially, if the memory is all well defined, like you know that you're working tasks and each one of those are tensors, then life is much better, right? But it turns out that the languages that do dynamic are also precisely the languages that move away from data structures like tensors. They start using more dynamic data structures like trees and hash tables, and then now you're stuck in this like how do you organize stuff? Yeah, I don't have an answer for you on that. I think that's. Did you have a question? Okay. Okay. All right, so this is where we are. How many minutes do we have? Okay, so instead, I'm going to show you like our latest work, which builds off of this, right? So I think that this latest work would not have been possible that easily with the existing flows. right? We needed the chisel to kind of be there for it. So I'll talk about that for a little bit, and then I'll kind of finish up. Let's see. Just want to skip through this. All right, so essentially, when we were doing all this work, one of the things we found out that is, right, once when you try to do these optimizations, obviously we're going to introduce bugs, a lot of bugs in fact, right? And it was very unsatisfactory for us because we didn't know how to track down a bug, right? Basically, my student would come back and say, oh, I compared the memory state, it looks okay, right? That was very unsatisfactory. Like I wanted him to tell me exactly every wire is the value match what the software SSA value would have been, right? And so when he was trying to do that, or when they were trying to do this, the thing that they found most painful or most time consuming was essentially adding the probes, right? So for example, if you're generating a graph hierarchically in your hardware, in your Verilog module, the adder or whatever whose value you want is embedded maybe 10, 12, 20 levels deep in the hierarchy. And there's no way for you to say, I want to know what is the output value of this adder, right? So I basically inject a probe and then introduce the probe at every level of the module hierarchy and then pull it out and then connect it to like a debugger, right? And so that was very hard. And so we basically created a framework for that. Basically auto inserting like user-defined probe. So user says, I want to monitor this thing in my circuit, and this is the checker function I want to add to it. And we'll say, so be it. And we would build in like a debug core and then attach all the wires and then wire it up to all the probes on the inside. And then what we would do is we would take this whole thing and then map it to an FPGA. And then now at runtime speeds, we can now check whatever you want to check, right? And we would allow you to do this. So one of the things that makes kind of the hardware output really hard to analyze is the fact that compared to software, right, which you can do binary instrumentation, is that the main one is that in software, the state is fixed, right? Meaning, exactly these are the registers, irrespective of the program, this is what you're monitoring. Obviously, with circuit-specific registers, that's hard, right? For each program and application generating its own circuit, there's a gazillion different registers sitting out there that you need to monitor, right? So, and second, you're looking at a structural concurrent specification because the hardware is concurrent by default, right? Whereas software instructions sequentially running, you can kind of stop, throw an interrupt, you can do all kinds of things that that you could potentially. And finally, like I said, software is sequential, hardware is concurrent, and you kind of have to monitor this. So the way we do this is, just believe me that there are a lot of applications of this. Is essentially what we do is, we go through the move IR phase, we get to our IR, right? Once we are there, essentially we have like the user can define the nodes, right? And the nodes would typically be at the level of the LVM. So the user can say, I want to monitor this LVM off, I want to monitor the other LVM off. And they'll also define instrumentation functions. For example, one could be is to check if the load addresses fall in a certain range, right? So that could be one potentially. What we would then do is add what's known as a guard. So a guard is basically a separate module that essentially we synthesize the checking function itself. So there's a range 0 to 100. We would synthesize a function for it, right, and spit out the hardware. Next comes the cool part. What we would then do is add these wires in place, right? So we would add these probes. And the way we would add these probes is essentially through a soft connect network, which is essentially saying, oh, this is the node you want to monitor, add a portal or basically a name here. And then we would add another name in this guard as well. And then when the Chisel elaborates the circuit, what it will do is it will iterate over all the Verilog modules. It will see what is the common hierarchy of the module. It would introduce an extra port in each one of those modules, and then wire the whole thing up, right? So essentially, all of this expansion would kind of happen between within the Chisel compiler as it's expanding this node to Î², right? And so this is where now we can kind of leverage what the constructs and write these passes within Chisel, as opposed to an MLIR pass that would do the same thing, right? If you had to do an MLIR, then for each one of these nodes, you'd have to say, I want an extra port at the Î² level, and you'd have to redo that port, right? But now we didn't have to do that. We could just leverage the Chisel to do that. So we would then probe the signal. For each one of these signals, We would have shadow values or checking or whatever other values that would come from the DRAM. And then we would have this checker function, which is kind of user definable. Both will run, and then we call this a guard function. If it mismatches, you have the option of patching in a new value, a correct value potentially, so that the circuit, if this is buggy, can still continue to function. So one of the hard things is we don't want a hard stop, right? We don't want to stop the circuit if something bad happens, right? We want to note the fact that something bad happened and then let the circuit further run, because potentially there can be more than one bug in the system, right? And we want to track it all with like a single run. And so then we would patch it and then send it downstream, and then from there onwards it's fixed, and then the signal can kind of continue to go through, right? And so we had this work, and then we did this, and what we and then we would collect all this information, dump it to a FIFO arbiter DRAM, and then post analyze the data, right? And the main benefit with this one is that because you do all these checks in hardware, you don't have to dump out the signal values to DRAM. So you save a lot of bandwidth, right? And it's not just saving bandwidth for bandwidth's sake, right? When you're debugging, who cares about the bandwidth, right? It's mainly because we don't want to perturb the original circuit, right? If you're using a lot of bandwidth, what happens is that you start stalling the original circuit and you're changing the execution of the original circuit. We don't want to do that. And so the less bandwidth you consume, it's better that way, right? And you can do all the processing within the hardware, and you're dumping out a lot less data out, right? Because you're only dumping out the processed information, not the unprocessed signal dump, right? And so we built this, circuit debugger, right? And what we would do is we would iteratively, find the bug, right? So what we would be is it would be a trade-off, right? So you could either add a lot of probes, and the design becomes small because the FPGA resources are fixed, or you could add few probes, and then you could map a larger design. And we would dynamically do this. So essentially, for instance, time goes from left to right, right? And it's fully scripted. Y-axis is design size that you're mapping to the FPGA, right? And so when we initially start, lots of probes, really small design. So it's like finding a needle in a haystack, right? So we're just probing many things because we don't understand what's buggy. Once we start seeing, which probes are actually, problematic, we'll start tuning out the probes, and we start increasing the size of the design. So in this case, when I say the design is bigger, typically it means that we're unrolling more of the loop. So we're getting more and more, stamping on more and more executors, basically, right? And then, maybe a few hours later, half a day later, you might get design at 60% design, 40% instrumentation. And then finally, basically by the time a day elapses, maybe 2%, you would have verified a design that's 98% of your original, right? And so fully automated, basically start the script and go to sleep, wake up next day, you're going to get some validation that it matches.
So usually you feel that one of the reasons you want to send back data is because it changes the behavior. When you are reading from, let's say, the PCI.
DRAM, yeah.
Now, what happens is, initially when you have 40% instrumentation,
it will perturb a lot. Yes, that is correct. It will, right? So we're assuming that the bug does not disappear as we change the size of the insertion. That's absolutely right. This is purely best effort. Right? The main thing we're going for here is also note that we're only validating an execution, which means you only validated the run for that input. Obviously, if you gave a different input, different coverage, these results don't hold, right? Because the bug could change or not. But the whole point of this is you can unleash this in like a cluster and just try different inputs, different coverage, and then you have some confidence in it. Previously, what the HLS guys were just comparing in memory state. Like we dumped it all to the DRAM with the memory values match. But now you get every SSA value is the wire matching or not. So one of the interesting challenges with this one is when we translate the software to the hardware, the SSA value in the software does not match the hardware wire one-to-one. Because when you go through the hardware thing, you have now perturbed all over the place. So you kind of have to keep track of where this SSA register, where exactly did it map to my hardware, right? And so there are a lot of nitty-gritties like that you kind of have to deal with.
How is the diagnostic communicated to the user when you find it?
So typically, as we iterate towards this, so you're basically back propagating on your dependence graph. So it's basically backwards analysis. and you would find the first cycle and the first node where the deviation kind of occurred. And you would
a line number.
you would say the SSA register that went buggy, right, or mismatched.
And so you track the location information.
Yeah. As you go
to the wires.
Yeah.
So you can map it.
Yeah, which is not obviously perfect because there could be some crazy optimization where you now lost the information. It's not a perfect science, let's put it that way. There's a lot of nitty-gritty that you got to deal with here.
Is it correct to say like this is compared to Rivardo's post-simulation? Instead of that, you're doing actually.
So there are subtle differences in that in the course simulation infrastructure, the human being is kind of saying where the probes have to be inserted, right? In this framework, the human being is not. So I initially said the user-defined probe, but really at this point, because the probes are easy to insert and it's automated, we basically unleash a script on it. So bare bones 101 software design, right? Probe all the branches, all the control flows and stores. If that's buggy, then start propagating backward from there, right? Because you have the dependence graph, right? So you can just back propagate, find the dependencies, and just propagate back, right? So it's fully automated. So that's what I would say. Whereas in Rivardo, the human being is expected to understand the trade-off between how much to probe and how big should the design be, right? So they'll say, okay, I want this variable, this variable, this variable to be monitored, right? So that's where there's some sort of differences. Anyway, yeah, so this wouldn't have been possible without the Chisel because the Chisel is the one that's injecting the probes. All we are controlling is where the probes are injected, right? But the Chisel compiler is the one that's actually figuring out where the ports should be, figuring out how optimally the ports can be introduced and making all the connections up. Okay. All right, I will stop with that and then I'll get on. Thank you.
I actually have one question. So, in this diagram that you showed in terms of inserting the probes and propagating the value, does it make sense to talk about, using that for something like built-in test or asserts being inserted in the circuit and therefore making the circuit more robust kind of thing?
Yeah, you can obviously change this, and so the main thing is how expensive are these guard functions, right? So how expensive is this thing? Remember that there's this. The main challenge is the following. Previously, the circuit used to be like this, which means values here, value went up. So your pipeline is just this. Now you reject this. So see what's happening with C1. Signal has to go through this. Comes here. Potentially reading a value from the outside. Maybe you don't have to, maybe you have to. It has to run here. Then you'll have to check and potentially patch. Each one of these is configurable. Maybe you don't need this. Maybe all you're checking is assert if it's 0, right? Maybe you don't need to patch. If you don't care about patching, you just want to stop the whole circuit, right? So you can remove it. But each one of these is going to port on the timing. For instance, without the probe, our circuit probably runs at like 300 megahertz and so on FPGA. With the probes, it maybe runs at 100 or 50. You just lost a 4x or 5x, right? So it's up to you to be very cognizant of this. We're not saying anything smart about that. Right? I'm not telling you how to minimize the cost of this function. Right? And so that's where this is like. So asserts probably maybe are cheap. You can just stop the world if something bad happens. So that's the answer to that.
When you are checking the output via the guard function, right? Sometimes even if you have the correct values, the values of in hardware, the values also need to come at the correct time. Time, you mean?
Yeah. So that's where the dynamic flow helps, right? Because all of these are very valid interfaces.
Oh, okay.
Yeah. If there's a cycle, then absolutely. Right. Typically, you can get around it by just saying this is one cycle and take the clock cycle hit. Right? Just take the hit. Right. You're going to run 10 times slower, who cares? Still faster than simulating, CPU.
Let's try to close the talk here, and students will probably interact with us in some more time.
Okay.
Let's thank Arrvindh again, and on behalf of the class,
Oh, thanks. think I still have the old one.